Today, I want to look at a number of different methods that are used to tackle a growing problem in the electronics and hobby community. What is that problem? Well, let's have a look. In the early stages, we had the old TTL chips all running at 5 volts quite happily. And later on came CMOS-based chips, which could run at 12 volts or 15 volts. And then he brought along microchip PICs that were designed to run at 5 volts. And then he brought a range of other microcontrollers based on the Atmel range, the Nano and the Uno and the Mega and so on. Again, designed to be running at the 5 volts. But then along came other microcontrollers like the Pro Micro, then later the Raspberry Pi Picos, which were running at 3.3 volts, and then a whole succession of input and output devices like the screen and the 2.4 gig transceivers, and which are running at 3.3 volts. And then even temperature sensors running at 2.7 volts. Of course, if you always only connect a 5 volt device to another 5 volt device, there's no problem. If you always connect a 3.3 volt device to another 3.3 volt device, no problem. If you connect a high voltage device to a lower voltage device, that there's a danger. You'll see some people on the internet that say, just give it a go, it'll probably work. And that can be true, but I wouldn't risk it. You're liable to either damage a low voltage device, or it may appear to function but give erratic results, or shorten its lifespan. So what are the different methods to get proper communication, which is called level shifting? We'll start looking at some of the most simple ones and build from there. So we have all these possible combinations connecting low voltage devices to high voltage devices and getting high voltage devices to communicate with low voltage devices. All kind of permutations, and you may ask, is it possible just simply to run them all at the same voltage anyway? And that's partly true. Let's look at this microchip PIC running at 5 volts, communicating with a 3.3 volt input. Can we not simply make the PIC run at 3.3 in the first place? And we can. With this particular microchip PIC, as you can see, although it's designed to normally work at 5 volts, it can happily work down to 2.3, so it can easily do the 3.3 volts that would be necessary to ideally communicate with a 3.3 volt device. So the inputs and outputs on both devices are now working at the same voltage. Problem solved. Of course, that is not always possible. So another approach that doesn't require any additional components is to check whether the 3.3 volt device is 5 volt tolerant. What do we mean by that? Well, it means, does the 3.3 volt device have internal circuitry, like clamping or whatever, that allows it to nevertheless accept 5 volt as an input? You have to check on the devices themselves. For example, the Pi Pico is not 5-volt tolerant. You have to make sure you only have maximum of 3.3 volts on the inputs. Whereas the LCD screen, some are 5-volt tolerant, despite running at 3.3 volts. Some are not. You have to read the specs. What if we want to connect the output of a 3.3 volt device into a 5-volt device? That would seem a reasonable thing. The output swing is probably enough to be registered as highs and lows on the 5-volt device input. But you've got to bear in mind that it's quite likely that the 5-volt input pins are held high to 5 volts with internal pull-ups. So unless you know a particular combination is safe, this should be avoided. Now, if we can't do any of these, we have to look at methods that involve components between the various devices. And one option is to use relays. To be honest, they're useful where a microcontroller has a small current output that has to drive, say, heavy motors or other high current equipment. They're useful, and you get complete isolation between the low voltage and higher voltage modules. But really, they're pretty large. And more importantly, they're very slow to operate compared to electronic components, which means they're useless for anything we have to have fast reactions or data communications. So we're looking now at other methods to connect between different voltage level devices. Let's begin then by looking at how we'll convert signals at 5 volts on the output down to 3.3 on the input. And you'll quite often see this, simply putting a series resistor between the output and the input to drop some of the voltage across that resistor. And that's fine if you see it in a magazine or a schematic where someone else has worked out the safe level and you know you can do it that way. But otherwise, there are better methods. The series resistor has to take into account the internal impedance of the input device, which you may not know. And you have to be sure that you don't put in excessive current into the input pin. Usually no more than 1 milliamp. The Mega chips have internal clamping diodes, but the Pi Picos don't. And therefore you have to be very careful we don't overload the input devices. So this isn't the best way, and we'll look at other methods. Another and safer method using resistors is the voltage divider. As you'll see here, the output goes to 0 volts via 2 resistors in series, and you tap off from the common point, and depending on the values with the output voltage will be configured. So in that example, the output of a 5 volt output pin goes through two 10Ks. They're the equal value, therefore the midpoint must be half, i.e. 2.5 volts. But we want to interface to 3.3, so typically then, if we used 2.2K and 3.3K, the 5 volts works out at more or less 3.3 volts. And there's no danger of problems with either the output or the input of the two devices. Of course, this only works when reducing a higher voltage level down to a lower voltage level. We can't use that the other way around to interface 3.3 up to 5. For that, we can look at using transistors. Here we have two examples using a transistor to interface between the two modules. In this example, we're using a MOSFET. But as you can see, that small circuit of only a couple of components allows us to both increase voltages between low and high and decrease between high and low. So it works out very well and has got little or no effect in general on the output or the input of the modules, assuming that the input of the 3.3 device is a high impedance input. The transistors are commonly used to communicate between modules of different voltage. But if you want complete isolation between two different modules, there's one other way that's commonly used, and that is optocouplers. The optocoupler has got no electrical connection between the input and the output. I don't intend to go into it in great detail because there's a video I made a year ago that you can access on the WOZAG YouTube channel. Suffice to say that the LED inside the optical coupler can be illuminated or not by the left-hand device. The light would hit the photodetector that would then feed into the right-hand device there. In that example, a high voltage device illuminates the LED, but of course we can have the opposite. So a low voltage device illuminates the LED. I can therefore switch the input of a higher voltage device. If we want to, we can have an inverted output or a non-inverted output, depending on how we configure its resistors. Here are a couple of working examples. You'll see on the left a microcontroller. It's running at 3.3 volts or 5 volts. It's trying to switch a 12-volt relay. It can't do it directly. And the safest way is shown in that example. And then we have one of our own pocket money kits, the DCC track detector. And you'll see that we are using the DCC signal itself to power the module. So I've got a pretty high voltage coming into the optocoupler. But because we are coupling it optically, the output could happily go to a 3.3 volt device, 5 volt device, or whatever quite safely. So we've looked at a number of methods, and they all have the one thing in common. They're all unidirectional. They go from one side to the other, either high to low or low to high. But in datacoms and networking systems and so on, we're looking at two-way communication. So how can we make the same wire transmit both directions? We're looking at bidirectional systems. For example, when I was looking at building EasyBus, I had to connect a Pico at 3.3 volts to an existing bus system on I2C working at 5 volts. How can I connect them when I'm expecting data to go in both directions? The SDA pin has to both send data and receive data. Well, Philip's application note shows it this way, but let's break that down a little. The circuit is using MOSFET transistors like this, 3-pin device operating when the gate becomes more positive than the source, allowing current to flow from the source to the drain. And then they're connected like this. The pins have pull-ups to the respective polarities. 10K is between the source and the low voltage, 10K between the drain and the high voltage. Consider the case when both module I/O pins are high. The gate will be at 3.3 volts, and so will the source. So the MOSFET will not be conducting, and in effect, it's as if it wasn't there. In which case, the pull-ups hold both pins high. So now, if you want to connect a 3.3 volt device to 5 volts, we bring the 3.3 output pin down to 0 volts. Now, there is a voltage difference between the source and the gate, which means that the MOSFET will conduct, and that in turn will bring down the input pin of the 5 volt device to 0 volts. And the inverse, if you want to connect 5 volts to 3.3, as per this, and we bring down the 5 volt device output pin to 0 volts, because of the diode that you see built into the MOSFET, there'll be a 0.7 voltage drop across that diode, and that's enough to switch on the gate of the MOSFET. And once again, MOSFET turns on, and once it's on, it's held on by the 3.3 volts and conducts such that the input of the 3.3 device also goes to 0. Typical MOSFETs for this purpose are shown here. Pretty cheap and handy if you only have 1 or 2 to interface. If you have greater needs, then you can buy these little boards. In this example, we have 4 bidirectional MOSFETs in operation, surface mount, so the board itself is pretty small. £3.30 for a single one, but if you buy from friends in China and buy in quantity, it drops to about 70 pence. And you can see a bit more clearly there what's on it, the individual MOSFETs and their respective pull-up resistors. I had the occasion to test multiple boards and so built this little tester. The board has a 12 volt supply coming in, and then on the left hand side I've got a 3.3 volt voltage regulator, and on the right hand side a 5 volt regulator, and the copper wires coming out are the inputs and outputs for testing. So let's see it in operation. So here we have it. If I put the meter onto the low voltage end, 3.3 volts, but if I bring this pin low, it drops low. Where I go high, it follows it. Same with the other pin, currently high, drops to low. And if I reverse it and check on this side, we're getting 5 volts, bring it low. If I bring this input low, let go, it goes high, go to that output, 5 volts, bring the input low, output goes low. And here's how I connected the Pipe Eco to the EasyBus using that module. You should be aware that there are other options. Look at this. On the right hand side we have the usual 4 MOSFETs, but on the left hand side we've got 2 MOSFETs and a bunch of resistors. There it is, the MOSFET with its pull-ups, but also a voltage divider. So it's a combination of MOSFET and the voltage divider. You should also be aware that you can get them in 8-channel. Again, using MOSFETs, but also you can have multi-channel level shifters using ICs. You can buy the IC on its own, or you can buy it as a surface mount on a board. And again, 8 channels, bit different. The chip expects to be told whether the direction is going from high to low or low to high by changing the voltage on the direction pin. So there we have it, a range of approaches and components to allow you to interface devices that work at different voltages. You just select the best method and the best module that suits your particular needs. Okay, see you next time.